Assalamualaikum. My name is Muhammad Daniel bin Muhammad Hamdan. My group member is Atan Dihang. We are from group 2. Our title project is accounting sequence 1350R71. Alright, so this is a state diagram. So you can see all the number is a binary number. 001 is a 1, 011 is a 3, 101 is a 5, 111 is a 7. Until that, you can see after you convert decimal to binary, you can get the same answer.
Next is the nested truth table for our group project title 13571 sequence. So here we have the current state with 1357 in decimal, and in binary is for 1 is 001, 3 is 011, 5 is 101, and 7 is 111. And for other numbers like 0, 2, 4, 6, we use the symbol cross to represent don't care it because it's not inside our group project title. And we need to know the next step for the sequence. So after the 1 is next step is 3, and the 3 in binary form is 011, and the flip flop input for D2, D1, D0 is 011, same as the next step binary form. Also for the next step for 571 is same for the flip flop inputs. After we did the truth table and we go to the corner maps, K maps. So for the first D4 is the D2, and we get the Boolean equation is D2 equal to Q2 and the SO Q1. So the D2 is a SO get. For the second D flip flop is we get the Boolean equation is D1 equal to Q1 bar, and it is D1 is a NOT get, and the third flip flop is D0 equal to Q0, and because of the all the D0 is 1 as in the truth table also, so we can determine it the D0 is 1 is the logic 1 and it is connected to the VDD. And because of this 3-bit counter, so there are 3 D flip flops. So next is the 3-bit digital synchronized counter circuit diagram after we did the truth table and the K maps. So here the FF0 is represent the D0 and it is connected to the logic 1 is the VDD. And second is flip flop is represent the D1 flip flop and it is the NOT gate connected to the NOT gate. And the third flip flop FF2 and it is the D2 flip flop. And between the FF1 and FF2 flip flop is connected with the SO gate. And all the 3 flip flops we will connected to the clock signal.
Alright, so we go to the next presentation about a Verilog code. Alright, so this is equation for D0, D0, always one logic height. Assign D0 equal to 1 binary 1. Equation for D1 is a inverter gate. Assign D1 equal to OQ1. Alright, so if you see the equation, this is a O gate. Equation for D2, XO for Q2 and Q1. Alright, so this is a XO gate because this equation have this symbol. Alright, so we go to the demonstration VCS analysis. Yeah. So I open the remote window. Okay, you need to go write the code about the waveform for VCS. Alright, so you can see this is a Verilog code for the counting sequence 13571. Alright, so next. Alright, so this is a test bench code for the counting sequence 13571. Alright, so you close the window. Alright, so still have zip up to date. Right, after you write the step by step for the guideline, you can see this is a DCE window for the counting sequence synopsis for the 13571 bit 71 in decimal value. Alright, so firstly you need to go to the test counting sequence, do right click, and then you go the add to waveform and new waveform. Alright, so you can see click button of OK. You need to maximize the window and then go to the you need to signal and get all signal. Okay. After that, you need to run the signal, the waveform. So you can see this is after you click button of run. Here you can see the transmission signal output for the output signal. Alright, so you need to unzoom the waveform. Alright, so after you unzoom, you can see. Alright, sorry. Alright, so you need to read from Q2 until Q1, Q0. Alright, so 1 is a decimal, convert to binary is 001, 3 is 011, 5 is a 101, 7 is a 111 until finish the output signal. Alright, so this is output waveform for the test bench counting sequence for the 1357 mode. That's all for me. Thank you.
Next, I will demonstrate the DC analysis for our group project. We open the remote Reaper and open the synopsis inside the remote PC And after that, we open the terminal, and we need to directly to our file we did for our group project. So cd platform, we did our project inside the lab work file. Inside the lab work file is the syntaxes and then passport for our DC analysis file. After that, we need to set up the synopsis DC. We use gedit of synopsis underscore DC dot setup, and this is the set that required from the table 2 design constraint for our group project instruction. Okay, we need to open the design vision GUI. So inside the design vision GUI, we need to enter all the requirement inside the design vision terminal. And after we enter the all value required, and it will come out the schematic diagram for the 3-bit counter. Then inside the design vision GUI, we need to enter all the requirement in the table 2 project design constraint about the design name, farm name, target library is scene 90 nm underscore slow.db, and also for the link library. Then the symbol library is generally.sdb, and library path is inside the link. Then we need to set up the clock period, input delay, output delay, clock transistor time, input signal transistor time, output capacitor is 0.001 pf, and the earlier we need to make sure is smaller possible size. After we enter this all value inside the design vision terminal, and it will come up the schematic diagram. And this schematic diagram come up in the DC synopsis is verified that same as the 3-bit counter circuit diagram we did manually. After that, we go back to the synopsis virtual machine, and we go to the home file, we find the lab work, and then we go to synthesis, task 4. So this file we did inside for the DC compiler analysis. So inside here there are lib, netlist, libos, script, and source file, and folder, and also the file with our group project title. So we go to the lib file. That is the library file, and is a scene 90 nanometer underscore slow.db is same as the table 2 project design constraint given. Then netlist, we have the DDC, SDC, and the very local file. After that, for reports, they are the 4 main report we need in our group project instruction. They are earlier, cell, clock, and timing reports. Next, we go to the script. This is a constraint.tcl and the run TCL that we set from the table 2 design constraint requirement. And the source, we have the very local. So our file name is for the very local is counter underscore 3-bit. So now we go back to the terminal inside the synopsis. Now we need the network synthesis. So here is the TCL file we set from the table 2 project design constraint. After that, we go to the report folder, and we need to use the gedit to check each of the report output. So first we check about the timing report. So inside here is the output generator automatically, and we scroll down and we get the time is flat, MET is positive 2.94 for the timing report for our counter 3-bit DC analysis. After that, we can check also the earlier, and inside the earlier show is 79.24 unit. Then is the report time is 5 nanosecond, and also for the cell report. So we have total 3 cells in our group project title, GD DC load, and this is our final DC load design compiler graphical file. And we get that our synthesis is complete and successful. That's all for me. Thank you.